In this lesson, we will discuss triangles and the properties they have. First, I'd like to state a fact that you may have heard before. The sum of the measures of all angles in any triangle, like these three down here, is always equal to the same thing, and that is 180 degrees, every single time. Let's try using this fact to find the measure of the missing angles in the triangles below. Starting with this one here, first of all, it appears that this is a right angle, so I'm going to draw in that this angle here is 90 degrees, represented by this symbol, so I'll put 90 degrees next to it. This angle is definitely less than 90 degrees, but I'll say that for this angle here, its measure is 60 degrees. If you know these two angles and this fact here, can you find the measure of the missing angle up here, which I'll call angle A? Our goal is, can we find the measure of this missing angle? It must be that if you add these three numbers together, their angle measurements, you get 180 degrees. You want to put a number here so that when I add 90 and 60 to it, it's 180. And that number is 30 degrees. So the measure of angle A is 30 degrees, and that's because 90 degrees plus 60 degrees plus 30 degrees is equal to 180 degrees. First, a little terminology about this triangle here. This is called a right triangle. Any triangle that has one right angle in it is referred to as right. So this is a right triangle. Okay, now what about this triangle? This is definitely not a right triangle. There are no right angles in it, but I'll make up some measurements. Let's say that the measure of this angle here is, we'll say 57 degrees, and maybe this one up here is equal to 41 degrees. What can we say about the measure of this angle here? So I'll call this angle B. While this one was pretty easy to do mentally, this one isn't as obvious, but if you'd like to figure out the measure of angle B, one approach you can take is take the total number of degrees, which is 180, and subtract off the two other angle measurements. What is left over must be the measure of this angle. So I'll do this in my calculator. 180 minus 41 minus 57 is 82 degrees. So that is the measure of angle B, 82 degrees. Notice that in this triangle, all the angles are acute, meaning they are between 0 and 90 degrees. If this happens, we call this triangle an acute triangle. So that's because all of the angles are, in fact, acute. Okay, last triangle here, this one. I'll make up two more angles. So maybe the measure of this angle, it's obtuse, so I'll do something like 120 degrees. And then this is a acute angle, so this one we'll say is 19 degrees. Can we use this information to, again, figure out, I'll call this the measure of angle C. I'm going to use this approach up here just because I'm not as confident with these numbers. So the measure of angle C, it's equal to 180 degrees minus 120 degrees minus 19 degrees. And the result that is left over is 41 degrees. And so that's the measure of this angle here. Notice that in any given triangle, there can only be one obtuse angle, one that is greater than 90. And the reason for this is if you had two obtuse angles, the sum of the angles would be more than 180 degrees, which is impossible. But if there is exactly one obtuse angle in a given triangle, well, we refer to that triangle as an obtuse triangle. So just a couple of terms to describe these different types of triangles by their angles. Now that we have applied this fact 3 times, why is this true? Why is it that when you add the angles in any triangle, the sum of the measures is always 180 degrees? And is this a coincidence that this is the same number of degrees that spans a straight line? So if you were to rotate from here to here, you also get 180 degrees. We will look at this on the next slide. All of the geometric topics that we have discussed in this chapter can be classified as Euclidean geometry. And that is a very fancy term to say geometry done on a flat surface, like a piece of paper. It's named after the mathematician Euclid, who lived around 300 BC and wrote the famous book, The Elements. The Elements is one of the most famous historical texts. It contains information about geometry done on a flat surface and a whole lot more stuff too. For example, when I decided to major in math, I had to take a proofs course. And one of the proofs that we studied was that there are infinitely many prime numbers. Now, Euclid proved this and put it in the Elements. And the proof that Euclid did back in 300 BC was the same one that I studied when I got my degree. So it's pretty incredible. Something that was true back then, still true today. Okay, all that being said, one of the things that was in the Elements is the parallel line postulate, which is an axiom. What this means is you can't prove that this is true, but you instead assume that it's true. And from this, you can prove other facts. It is important that this is a reasonable assumption. So after I describe it, hopefully you agree that it is in fact reasonable. So here we go. The parallel line postulate stipulates that if a line and a point not on that line are drawn on a flat surface, then you can draw a new line through the given point that is parallel to this first given line. Now that is quite a bit, it's quite wordy, but here's what it's saying. You come along and you draw a line and then a point that is not on that line. So that's this part and this part. This axiom says I can show up and draw a line that goes through this point that is also parallel to this line. And so that would look like this. So this is what I can do with the stuff that you drew. This being parallel to this means these two will never intersect. In fact, this is the only line that you can draw that is parallel to this one going through this point. So there's exactly one line like this that you can draw. Any other line that would go through this point on a flat plane would always intersect the very first line. So that's it. That's all this says. It is assumed to be true, and it does seem like a pretty reasonable assumption. With this stated as an axiom, we now can prove the following theorem. For any triangle that's drawn on a flat surface, the sum of the measures of the interior angles is 180 degrees. I will label the angles of this triangle as 1, 2, and 3. So here's angle 1, here's angle 2, and here's angle 3. What we are trying to prove, what we want, is that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180. We don't know that this is true, but this is where we want to end up. If I want to use this axiom on this triangle, I want to first draw a line and a point that's not on the line. I'm going to choose to take this side of the triangle and extend it forever in both directions, essentially creating this line. So that will look like this. So here we go. This goes forever in both directions. And a point that is not on this line is this one right here. So I'll draw this point here. This axiom says that we can draw a line that goes through this point that is parallel to this line. And in fact, it is the only line that exists that satisfies this condition. So I'll draw that line like this. So here it is, and that's by the parallel line postulate. The thing to note is that the measure of the angles going from here to here is 180 degrees, and that's because it's a straight line. Notice that we've created two more angles. I already have 1, 2, and 3, so I'm going to call this angle 4 and angle 5. So we got angle 4 and angle 5. We know for sure that the measure of angle 4 plus the measure of angle 1 plus the measure of angle 5 is 180 degrees. So I'll write that down. The measure of angle 4 plus the measure of angle 1 plus the measure of angle 5 is 180 degrees. We're trying to go from this statement to this one, And notice that there's something in common to both, the measure of angle 1. I'd somehow like the measure of angle 4 and 5 to go away and be replaced with the measure of angle 2 and 3. Maybe there's some way to connect the measures of angles 4 and 5 to the measures of angles 2 and 3. And there is a way to do this. You can draw a transversal here. That is a line going through two parallel lines. On this transversal, alternate interior angles are equal. That is the measure of angle 4 and the measure of angle 2. They're the same thing. The measure of angle 2 is equal to the measure of angle 4. What about the measures of angle 3 and 5? Are those equal? Sure. We got this other transversal right here. The measure of angle 3 is equal to the measure of angle 5, again, because they are alternate interior angles. This one is equal to this one. All right, we're basically there at this point. Here, I can replace the measure of angle 4 with the measure of angle 2. I can just swap this in because they're the same thing. Likewise, the measure of angle 5, I can replace that with the measure of angle 3 because they're equal as well. So if this statement is true, combined with this information, I can write, instead of the measure of angle 4, I'll put the measure of angle 2, then plus the measure of angle 1. Now instead of the measure of angle 5, I'll put the measure of angle 3, and I still get that this is 180 degrees. If this equals 180, then this must as well. But the order in which you add the measures doesn't matter. You could reorder this as the measure of angle 1, then the measure of angle 2, and then the measure of angle 3, and it still is equal to 180 degrees. So as a matter of fact, this proves that in any triangle, since you can always do this process, if you sum the measures of the interior angles, the ones on the inside of the triangle, you get 180. In example 2, let's find the measures of angles 1 through 5. So where to start? Over here we have a triangle, but I only know one angle, so I can't solve for the other two. But over here, this is a right triangle, meaning this is 90 degrees, this is 57. I have enough information to find the measure of angle 1. Let's start there. The measure of angle 1, I know the sum of the angles is 180 degrees. Therefore, if I subtract 90 and also 57, the remaining number is the measure of angle 1. And so when I do this arithmetic, I get that the measure of angle 1 is 33 degrees. Notice also that since this is 90 degrees, the other two angles have to add to 90 degrees. 90 plus 90 is 180. So angle 1 and this angle are complementary. They add to 90 degrees. You could do that to get to 33 a little bit faster if you'd like to. Okay, so we have the measure of angle 1. This one's done. What can we figure out next? We could go to either angle 2, 3, or 4. I think we know how to find all of those. I think the simplest is the measure of angle 3. I'll do that one next. Angle 1 and angle 3 are vertical. They are vertical angles. And therefore, their measures are equal. The measure of angle 1 is equal to the measure of angle 3. Therefore, they're both 33 degrees. So this one's 33. And this one is 33 as well. So I'll state that here. We have the measure of angle 1 and also the measure of angle 3. Now what about either the measure of angle 2 or 4? Angle 3 and angle 2 are supplementary. If you add those two angles together, that is a straight line, which is 180 degrees. So if you want the measure of angle 2, that's the same thing as saying take 180 degrees and subtract off the measure of angle 3. Of course, we know the measure of angle 3, it's equal to 33. And when you look at the difference of 180 and 33, you get 147. And therefore, this is the measure of angle 2. All right, so we know the measure of angle 1, 3, and now 2. I think next I'll figure out angle 4. Angle 2 and angle 4 are vertical angles. And their measures must be the same. So what's the measure of angle 4? Well, it's equal to the measure of angle 2, which we just figured out was 147 degrees, and therefore the measure of angle 4 is also 147 degrees. So we have that one. We are close to solving this whole problem because there's only one angle that is left to deal with, and that is the measure of angle 5. Angle 5 is in a triangle along with angle 3 and this angle here, which is 63 degrees. I know if we add these three together, their measures, you get 180, and we figured out 3. That means we can solve for the measure of angle 5. The measure of angle 5 is 180 degrees minus 63 degrees, and then the measure of angle 3 was 33 degrees. If we do that arithmetic, 180 minus 63 minus 33, we get 84 degrees. We have found the measure of all angles in this diagram. Let's now discuss the topic of similar triangles. For this topic, I thought of this image. It's called the Eye of Providence, and you can find it on the back of a $1 bill. So here I have two separate images. The only difference is this one is larger than this one. Although they are not exactly the same, you can say that they are similar. More specifically, that means the corresponding angles in this triangle are going to be equal to the corresponding angles in this triangle. The lengths of the sides, the corresponding sides, are different, but the angles are in fact the same. So if I draw this angle here, it's going to be equal to the measure of this angle here. Likewise, if you look at the angle here, whatever it is equal to, it's going to be equal to the measure of the angle here. And of course, lastly, the angle here is equal to the angle here. They actually have the same measure. The reason for this is, if you draw an angle, so here's your original angle, and you increase it going from one image to the other, all that's doing is expanding the length of the sides. It's just making this side longer and this side longer, and that's it. But it is still spanning the same amount going from one ray to the other. And for this reason, the measures of the corresponding angles are the same. We can now restate the definition of similar triangles. Two triangles are called similar if the measures of the corresponding angles are the same. They're actually equal in measure. And because the corresponding angles are the same, even though the sides are not the same length, and this is where similar triangles are different, the lengths of the sides are different, they are proportional to each other. That is, if you divide this side to this side, it has the same ratio as this side to this side, and this side to this side. We can say that the ratio of corresponding sides are equal. So the actual lengths themselves are not equal, but the ratios between them are. They're proportional. Now you might be curious, as I was, well, what are these actual angles that appear in the Eye of Providence? And on the back of the $1 bill, what's the length of each of these corresponding sides? When I first looked at this triangle, I thought it was an equilateral triangle, and that means all sides are the same length. And it turned out that when I measured them with a ruler, that wasn't true. There's two other possibilities if you talk about the sides of a triangle. If none of the sides are equal, that's called scaling. But there is another option, and that is if two sides are equal. That's referred to as isosceles. In fact, after I measured this, I found out it was an isosceles triangle. That means exactly two sides are equal in length or measure. And it was these two sides here. When I measured it, I found out that the one on the left was 5 millimeters, and then the one on the right was also 5 millimeters. But the one on the bottom was only 4 millimeters long. Now, suppose going from this image to the one with the longer sides but the same angles. Let's say when you increase the image, this now became a side of length 10 millimeters. So that is now the length of this side. Can you use this idea that the ratio between the corresponding sides is equal to determine the length of this side and this side? I feel like this one must be obvious. If this is isosceles, then so is this one. And if this side has equal length to this side, then this side must have equal length to this side. So, okay, well, this one, I think it's got to be 10. But what can you say about the corresponding side down here? What should its length be in millimeters? Well, what we're doing here is we're taking 5 and we're doubling it to get to 10. So when we talk about the ratio, that is 10 divided by 5. Ratio being fraction, you're literally dividing the two sides. And that reduces to 2 to 1, and you can think of it as just 2. That's the same ratio of this side to this side. 10 divided by 5 is also 2. Or 2 times 5 is 10. What must be the length of this side? I'm sure you may have guessed it. It is 8. And the reason is, if you take 8 and you divide it by 4, the length of its corresponding side, you get 2 over 1, or 2. So here, the ratios, when you divide, of the corresponding sides reduce to the same number. Of course, you could do this backwards. You could do a ratio of 5 to 10 instead of 10 to 5. Your ratio would be a half, but when done this way, the ratio of all the corresponding sides would be a half. Whichever way you do it, it has to reduce to the same number. So that is everything I wanted to say about the sides. Still though, what are the angles here, here, and here? I had to figure those out, and I have approximate values for them. This angle here, I got approximately 66 degrees, which means that's the same as this angle here. For the angle at the top, the one that is in red, I figured out that that was about 48 degrees, so roughly 48 degrees. So 66 degrees and 48 degrees. Do you know what the other angle must be equal to? In terms of discussing similar triangles, it actually really doesn't even matter. Since the sum of the angles has to equal 180 degrees, if you know two angles, you can always find the third one, and if these two are equal, then this third one must be equal too. We define similar triangles to be triangles whose corresponding angles are equal. So you need all three corresponding angles to be equal to each other. But the second that you know two corresponding angles are equal, it must be that the third is equal as well. This brings me to the following important fact about similar triangles. Two triangles are similar if they have two corresponding angles that are equal in measure. And that's it. So the second that you have two angles that have the same measure, the two triangles are similar. You don't even need to know what the third angle is. I will state it here though, since this is an isosceles triangle, it's got to be that this other angle was also 66 degrees, equal to the one on the opposite side. In the next slide, we will apply this fact here to show that two triangles are similar. In example 3, I'd like to explain why these two triangles are similar, and then once we do, I'd like to solve for the lengths of the missing sides in the larger triangle. So first of all, are these triangles similar? And the answer is yeah. They have two angles, corresponding angles, that are equal in measure. This one's 25 and that one's 25. Likewise, this one is 75 degrees and this one's 75 degrees. I think I'll put a mark here and here to indicate I'm talking about those two angles, and then 2 marks here to indicate that I'm saying that those two angles are equal in measure. So to reiterate, these triangles are similar because they have two corresponding angles that are equal in measure. And once you have two corresponding angles that are equal in measure, you get the third one for free. Okay, so now let's solve for the missing sides on the larger triangle. And I guess we're talking about the lengths of these sides. So for example, if I call this one x and this one y, what numbers correspond to the lengths? I can see from this side and this side, the ratio you could consider as 10 over 20, which is a half, or 20 over 10, that would be 2, and that gives us the ratio. We can use whichever one we'd like. I'm going to take the approach of setting up a proportion to solve for both x and y, and I'll start with x first. So I think I'll do the ratio of this side to this side set equal to the ratio of this side to this side. What that looks like is the ratio of 20 to 10 is equal to x to 9. So here in the ratio, if this one's in the numerator, then this one's in the numerator, and if this one's in the denominator, then that one is in the denominator. To solve for x, I'd like x alone on the right side of this equation. It's being divided by 9, so what I'm going to do is multiply 9, or 9 over 1, to both sides of this equation. The 9's on the left cancel to give us just 1's. So this is x times 1, which is just x. I don't need to write the denominator because it's 1 times 1. Perfect. On the right-hand side, we have x. On the right side, we have 9 times 20 divided by 10. 9 times 20 is 180 divided by 10. And if you divide 10 into 180, you get 18, and that is the length of side x. So what we have shown here is if you divide these two sides, the ratio you get is 2. Said another way, you can take this side and double it to get this side here. And really, I know that this side has to be equal to 8 if you double 4. Another way you can think about it is if you look at the ratio of the side labeled y to the side labeled length 4, I know the ratio of it has to be equal to 2, or 2 over 1. If you'd like to figure out what y is equal to, you can solve for it by multiplying both sides of this equation by 4. We're really doing the same thing in every single case. On the left side, it's really a fraction. You can cancel the 4's. It's just 1's that are left over. We have y is equal to 2 times 4, and that is equal to 8. In example 4, we will consider an application of similar triangles. This says, a person who is 6 feet tall casts a shadow that is 11 feet long. At the same time of day, the shadow of a tall building is 385 feet long. Can we use similar triangles to figure out the height of the building? So this would be an indirect way to determine the height. You wouldn't have to actually measure a vertical distance. You could just measure the shadow that the building creates. I'm going to draw a picture for this, a very basic one. I'll let this vertical line represent the height of the building, and this horizontal line represent the length of its shadow. And at this time of day, it's because the rays of light are coming in at an angle, and that would be something like this. So this is a right triangle, and this is 385 feet for its shadow. What I don't know is the height of the building. I'm going to call that x, eventually something we would like to solve for. Now, likewise, at the same time of day, meaning the rays of light are coming in at the same angle here, there is a person who is 6 feet tall, and their shadow is 11 feet. And this is certainly a right triangle, and the rays of light create an angle here. This angle is equal in measure to this angle, and that's because this is happening at the same time of the day. Now, how can we use similar triangles to determine the height of the building, the thing that we don't know? Well, these two triangles that I have drawn, are they similar triangles? And the answer is yes. They have two corresponding angles that are equal in measure. This one's 90 degrees and this one's 90 degrees. That's given information because we have a vertical and horizontal line. And also, this angle is equal to this one because this is happening at the same time of day. So these triangles are similar. If we know this piece of information, corresponding sides have the same ratio. So the ratio of this side to this side is equal to the ratio of this side to this side. This will allow us to set up a proportion. X divided by 6 is equal to 385 divided by 11. I'll write that off to the side. The ratio of x to 6. Now, I don't know what this is. That's okay. It has to be equal to 385 divided by 11. To find the height of the building, that is equivalent to solving this equation, this proportion for x. And to do so, I can multiply 6 to both sides of this equation. That's 6 divided by 1 multiplied to 6 divided by 1. On the left side, the 6's cancel, they're all 1s. The entire left side is just x. It's x times 1, which is x, divided by 1 times 1, which is 1. On the right, this is 385 multiplied to 6, all divided by 11, which I'm going to do that in my calculator. Okay, so 385 times 6, 2,310, then divided by 11 is 210. And the units on this have to be feet, because that corresponds to the unit used for 6, 11, and 35 in this process. So here we have an indirect way to determine the height of a very tall building without ever measuring a vertical distance. All the measuring can take place along a horizontal surface. The last topic in this lesson is the Pythagorean Theorem. This is a very important fact about all right triangles. In fact, this theorem states that in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the remaining side. What does that mean? If I draw a right triangle like this, and it's a right triangle, so that's the 90-degree angle, if I label the hypotenuse C, and the other two sides, which are called the legs, A and B, this says if you square C, if you square its distance, it is equal to what happens if you square these two distances and add them together. That's a squared plus b squared. Of course, you could also write this as a squared plus b squared is equal to c squared, which is commonly how it is stated, although you could write it this way too, no problem. This fact will allow you to solve for a missing side of a right triangle if you know two of them. A basic example of this would be if you had a right triangle and one side was length 3, another 4, and you didn't know the length of the hypotenuse, which I'll call C. This theorem will allow you to solve for this side. I will call this side A and this side B. According to, I'll use this equation here, c squared is equal to a squared, which is 4 squared, plus b squared, which is 3 squared. So c squared is equal to 4 times 4 is 16, 3 times 3 is 9, and 16 plus 9 is 25. So we just solved for c squared. Not c, but c squared. Can you think of a number that when you square it, it's equal to 25? If you can't, that's okay, because there's an operation you can use to solve for c, and that is taking the square root of c squared. If you take the square root of c squared, the square and the square root cancel to give you c, and then the square root of 25 is 5. And this is another way of saying 5 times 5, or 5 squared, is 25. So if you have this function on your calculator, it's nice because it can find square roots for you very easily, which is the last step in this process. Sometimes the number doesn't come out nice, it comes out to a decimal, and having a square root function on your calculator can be nice to get a good decimal approximation. So let's apply this theorem in example 5. Example 5 says if you travel north for 12 miles and then east for 22 miles, that is a total distance of 34 miles that you traveled. So I'm going to draw a picture of that. So let's see. we go north 12 and then east 22. So here's 12 miles, here's 22 miles. So if you're in a car or a bike or something like that, it's 12 plus 22, the total distance you traveled. If possible, if you could travel along this path here, this would be a shorter distance if you were on a flat surface. And this is a right angle. Well, what is this shorter distance? How far would that be? I'm going to call this side C. Because this is a right triangle, this theorem holds true, and we can use the fact that C squared is equal to A squared plus B squared, where I think I'll call this side A and this side B. Technically, it doesn't matter. You could reverse those. So C squared is equal to 22 squared plus 12 squared. I know that 12 squared is 144. I don't know 22 squared. Probably could figure it out. But in my calculator, I have that C squared is equal to 22 squared is 484. And as I said, 12 squared is 144. And therefore, C squared is equal to the sum of those two numbers, which is 628. Ultimately, you want to solve for C, not C squared, because that would tell you this distance. This one, you probably could do without a calculator. I'm not so sure about this one. So I'm going to take the square root of both sides. If you square root a square, and we're talking about distance, that's the same thing as saying C. The square root of 628, which I'm doing in a calculator, it actually comes out to 25.05992817. And this is in miles, because that's the unit of these two numbers here. If we round our answer to the nearest tenth as necessary, that's to this location, we get that C is equal to 25.1 miles approximately. So in this case, on this path, you've traveled 34 miles. This is definitely the shorter way to go if possible, and that distance is 25.1 miles. I guess the question technically asks, how much shorter is this distance? That is this from that. So I'll put, shorter. How much shorter? That would be 34 miles minus 25.1 miles. And if you take that difference, you get 8.9 miles. It is that much shorter if you go the hypotenuse instead of on the legs of this right triangle. One final thought, just in case if you're interested. We saw that if you draw a triangle on a flat surface, the sum of the angles in the triangle is 180 degrees. Is this true for a triangle drawn on a sphere or some other type of surface? Here on the equator, I have highlighted where Quito is in Ecuador, and then over here, you can't really see it, but this is Libreville, which is in Gabon. And these are both approximately on the equator, like this. If you follow a longitude line up, you'll reach the North Pole, so I'll draw a couple of those. Here's the North Pole, and here's a longitude line going up to this one, and then one going back down to Libreville, down here. Longitude lines and the equator are perpendicular to each other. Therefore, this is a right angle. It's 90 degrees. And the same thing can be said for this over here. And we have a third angle up here, and that means we have a triangle, literally 3 angles. I figured out that this angle was roughly 85 degrees. So in this triangle, drawn on a sphere, what is the sum of the measures of these angles? So the sum of the measures of the angles is 90 plus 90 degrees for the two right angles plus 85 degrees. and the sum of that is 265 degrees. That is greater than 180 degrees. So a triangle drawn on a flat Euclidean surface, the sum of the measures of the angles must be 180 degrees. But on other surfaces, like spheres, that is not necessarily true.